share screen. All right. We are cooking with something. Okay. 9.3 is matrices and systems of equations. So in 9.2, you did the elimination method, and where you learned to find an ordered triple XYZ that made all equations true at the same time. 9.3, you're going to do the same thing, but instead of in terms of equations, we convert it into what's called an augmented matrix. So we just have to learn the process, and it's basically the elimination method yet again. So because we're learning the same thing twice, on your final, most likely what will happen would be, unless I forget, there will be a question to where in part A it says solve it using elimination, and then part B will be solve it using matrices. And because it's the same exact question, meaning the numbers, you should get the same answer for both parts. So basically I'm building in a check. The problem with 9.2 and 9.3 is that as far as complexity and as far as everything we've done in this class, they're not terrible. They're just tedious problems. So if anything, at least there's a check built in to let you know that you did it okay. Before going any further, let's formally define a matrix. Now, this is going to be what the kids 10 years ago would call it cray-cray, because it looks horrifying. But I'll explain what all the symbols mean. A matrix is a rectangular array of numbers of the form giant brackets in the top left corner, A subscripted 1, 1. To the right of it, A with a subscript 1, 2. To the right of it, A with a subscript 1, 3. And then at the end, 1, n. And then the next row, 2, 1, 2, 2, 2, 3, 2, n. And this continues at the very bottom, m, 1, m, 2, m, 3, m, n. Oh my gosh. All right, we're over hurdle number 1. Where each A sub I, j is a real number, in this class at least, called an entry or element. The size or dimension of the matrix is m by n. So a lot to unpack here. Remember, rows go across, columns go up and down. So you can think about Greek columns if you want, the ones that are standing up. What about if they're laying down? We don't talk about those, just the ones that stand up. What the subscript is saying is the first number is the row that it's in. The second number is the column that it's in. So notice A sub 2 comma 3 is in the second row, third column. So a matrix is a very positional system. So I'm just making this matrix up. One, 4, 0, 7, negative 9, 6, 12, 8. How many rows does this matrix have?
2.
Good. How many columns does it have?
4.
Good. So we would call this a 2 by 4 matrix. We always write rows first and then columns. What row is the 0 in?
The first row.
And what column?
Third.
So this is the 1, 3 entry. Or the 1, 3 element, your choice. So the 2 by 4 tells you the size of the matrix, formerly called the dimension. And then it's always row by column. Okay. Questions? All right. So as far as what's happening in this section is in 9.2, even though we did 3 variables, we're going to start with 2 variables. In 9.2, you had a system such as 2x plus 3y equals negative 6, and x plus y equals negative 1. And then using elimination, you would solve for x and y. I'm going to just tell you what the answer is. And I'm purposely writing it like this. I'll explain why in a second. You got x to be, you would get x to be 3 and y to be negative 4. So the gaps are intentional. So that was section 9.2, or similar. In 9.3, in matrix land, what we're going to do is we're going to turn a system into what is called an augmented matrix. To augment something means to make bigger, to add on to. So if you've ever studied music theory, if you go from C to C sharp, you've augmented the note. You one up one. In this case, because we have two equations, we're going to need two rows in our matrix. And we technically have three columns because we have an X column, a Y column, and a constant column. So we are going to create a 2 by 3 matrix. 2 rows, 3 columns. The augmentation for us will be represented by separating the coefficients on the left and the constant on the right. And the augmentation is shown with that vertical line. So basically we slapped a 2 by 1 matrix to the right of a 2 by 2 matrix. So instead of the equation 2x plus 3y equals -6, we can now write the row 2, 3, -6. And likewise, instead of the equation x plus y equals -1, we can write the row 1, 1, -1. The benefit to matrices is we don't have to write the variables anymore. As long as we keep things in the right position, meaning x coefficients go in the x column, y coefficients go in the y column, constants go in the constant column, we don't have to worry about the actual variable itself until the very, very end of the problem. Now, truth be told, we're doing things on the extraordinarily small scale in real life. They're using computers because their matrices are like hundreds of rows, thousands of columns. And as far as where is this used, your delivery services are a fantastic example of use of matrices. We don't get into it in this class, but if you were a dietitian and you were managing your patients' protein intake and your carb intake, blah, 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 that could all be represented with a giant matrix. So each row could be a patient. Each column could be a macronutrient, I think is the proper term for protein, carbs, all that good stuff. We're sticking to at most 3 variables, not the amazingly good stuff, because we don't have time for that. So there's that. So in blue, in that matrix, we see the corresponding augmented matrix. What we're going to learn is a process called the Gauss-Jordan method. And in the Gauss-Jordan method, we will take our starting augmented matrix in blue, and we will get it to our answer matrix. And now this is why the gaps were there. So instead of the equation x equals 3, let's write the corresponding row. What's the coefficient of x in the equation x equals 3? Well, I apologize. So we're looking at this right now, and we're going to write the corresponding augmented matrix. So what's the coefficient of x?
The 1.
Yeah. What's the coefficient of y in the same equation?
There is no y.
There is no y, so the coefficient is 0. And the right-hand side is 3. And how about the equation y equals -4? What would that look like as a row?
Zero, 1, -4.
Very good. We have no x, there's one y, and the constant is -4. Awesome. So we already know how to do this via elimination. That's 9-2. Now we're going to do the same exact thing via this magical thing called Gauss-Jordan, which is 9-3. All right, so that's the setup. So the question is, how do we do that? I have no idea. Let's discover it together. I'm kidding. I know how to do this. No idea. We are allowed to do 3 things. And these are called your elementary row operations. You are allowed to swap two rows. And by the way, we're going to write some notation next to this. I don't know if you want to leave room in your notes. You are allowed to multiply a row by a non-zero number. And you are allowed to multiply a row by a non-zero number and add the result to another row. These are all legal. And just to discuss, the reason they're legal is because, for instance, the first one says you can write your equations in either order. X equals 3, y equals negative 4 is the same system as y equals negative 4, x equals 3. Notation for that would be r sub I with a double arrow r sub j. Multiply a row by a non-zero number. If you had 1/2 x equals 6 and you wanted to solve for x, you would multiply both sides by 2. Because as long as 2 is not 0, it's legal. And that's what number 2 is saying. So that looks like k times r sub I becomes the new r sub I. And number 3 was basically your elimination method. You would multiply an equation by a number, so when you added it to another equation, that variable would go away. Notationally, that's k times r sub I plus r sub j gives you r sub j. By the way, I'm going to tell you guys now, I think we might be going over today by about 10 minutes, so I apologize in advance. Okay, let's go through an example. There are already 3 example videos online. So there's plenty to look at, but we definitely need to see one. So suppose we had x plus, I'm so sorry. Suppose we had negative 2x plus 5y equals negative 26. Hold on. Don't write this down just yet. Hold on. I'm so sorry. X plus 2. I have a little X in my notes, and I don't know if that's a good thing or a bad thing. I think it's a bad thing. I think I'm going to change the number here. I think I'm going to change this negative 26. Ah, it's so hard to do in my head. 1, 2, 3. Let's make that negative 17. Alright, so negative 2x plus 5y equals negative 17. X plus 2y equals negative 5. So our first step is to turn this into an augmented matrix. Just like before, we have 2 equations, so our matrix will need 2 rows. And we need 3 columns, an x column, a y column, and a constant column. What's the first row of our matrix going to look like?
-2, 5, 7, or -2, 5, -17.
Good. And now cover your left eye and please read the second row.
0, 2,
Careful.
and then -5. Oh,
One-
1. That's
there
right.
you go. Very
1,
good.
2, -5.
I'm assuming you cover your left eye.
Yeah.
I believe you. Okay. That's where we're starting. Where we're ending is always the same. The goal is to get a 1 in the top left, and then diagonally going down to the right, another 1. So if we had a 3 by 3, there'd be a diagonal of 1s. Everywhere else needs to be a 0. And the numbers on the right-hand side of that bar will tell us our x and y's. So 1s on the diagonal, 0s everywhere else. The way we do that is, and by the way, what I'm about to show you will definitely work for every single problem. However, it may not be the most efficient, but I'd rather you teach a way that's guaranteed to work every single time than you doing something that works half the time. The way we do that is we ignore everything but the first column. So I don't care what's there anymore. Looking at the -2 and the 1, that column, and looking at our goal, you want to make your 1 first and then make your 0. So let's talk about how you would make that 1 first, and we'll go through all 3 of our possible row operations. We could swap the rows, and notice if we swap the rows, that would put a 1 in our 1, 1 position. So that's a completely viable, very easy to do operation. Number 2 says we could multiply the first row by -1/2, because -1/2 times -2 makes +1. But sneaky, notice that would make fractions at the 5 and -17, because you have to multiply all the way across. Now, working with halves is not terrible, but so far the first operation's the winner because there's no fractions involved. The third operation says we could be tricky. We can multiply the we can multiply the second row by 3, so that 1 would become a 3, and add it to the first row, because 3 plus -2 is 1. Gets the job done, but in my opinion, the easiest way would just be straight up swap the rows. Don't mess with anything else. Questions? Okay, so notationally, what this says is we're going to say row 1 swaps with row 2. So the new first row is 1, 2, -5. And the new second row is -2, 5, -17. So we got the 1 where we need it in the first column. Oh no. How do I... ignore the stuff in blue. Ignore it. It's not there. I don't know why this is happening. That's weird, right? All right. What are we going to do? That -2 now needs to become a 0. Here's the deal. The third operation is what you use to make zeros. You can't use anything else, because the third operation is your elimination method. So remember, this really represents 1x. This really represents -2x. What would you multiply the 1x by, so when you add it to the -2x, the -2x becomes 0?
2.
2. So using this notation, we're going to take 2 times the first row, take that result, add it to the second row, and that becomes the new second row. Questions on that? Okay, off to the side, and please do this off to the side. I highly recommend you write stuff down, because if you do too much in your head, you might forget a negative sign, you might throw in a negative sign, and there goes the whole problem. Off to the side, let's write down what 2 times row 1 looks like. So if I multiply the first row by 2 off to the side, we would get 2, 4, negative 10.
All right, Tamara. Quick question: Do you think you could add this to the playlist somehow? Because I think I might need to go over this, like, again, in case I forget.
Oh yeah, it's being recorded right now.
Okay,
We're
thank you, I
live.
appreciate it.
Yeah, no worries. We're going to take these green numbers, which is 2 row 1, and we're going to add it to row 2. And remember, this is row 2. So negative 2 plus positive 2 makes
0.
Go ahead. 5 plus 4 makes
9.
Good. And lastly, negative 17 plus negative 10 makes negative 27. And now to finish this off, I'm going to write in the previous row 1. Several comments. The reason I don't write in 2, 4, negative 10 is because I want to keep my 1. That's what we did the first operation for. And that's why we do the 2, 4, negative 10 off to the side, because that's just side work. Comment number 2. We have completed column 1, 1, 0. As we go on, this column should not change if you do things correctly. So one more time, all we did was we ignored everything but the first column. We made our 1, then we made our 0. Now we move on to the next column. I really wish do I have to right click on it? Oh, that's the dumbest thing. Is it orientation? No. Is it order? Bring to front. All right. I think that's all it is. So now we ignore everything but the second column. I don't want to make another rectangle. That was way too much work. So we have 2, 9. We need to get the 2, 9 to look like this column, 0, 1 in our goal. Same deal. Make your 1 and then make your 0. Now, one thing we cannot do is the following. You cannot say, oh, if I multiply the first row by negative 4, 2 times negative 4 is negative 8. Add that to the 9. That makes a 1. Coolio. The problem with that is you would lose your 0, because 1 times negative 4 plus 0 is no longer 0. So what happens in this process, unfortunately, is we paint ourselves into a corner. And so, meaning that in order to make a 1 here, where that 9 is at, we actually have to use the second operation. The second operation can make 1s. The reason the word can is there is because it doesn't have to make 1s. It can be used to make a 1, and that goes back up to the first thing. I could have multiplied the second row by 3 to add it to the first row to make a 1. Or I could have multiplied by negative 1/2 to the first row to make a 1. They both would have worked. But once you're in this, when you're stuck in this corner, you have to multiply by the reciprocal. So in order to do that, in order to continue, we're going to do 1/9 times the second row, and that becomes the new second row. So to make a 1, multiply by the reciprocal. The first row does not change. That still stays 1, 2, negative 5. In the second row, we're going to multiply through by 1/9. 0 times the ninth is 0. 9 times the ninth is 1. And negative 27 times the ninth is negative 3. So we got the 1 where we need it. So again, ignoring everything else, that 2 needs to become a 0. What operation do we have to use to make a 0? So this is currently saying 1y. This is saying 2y. What do we do to the 1y? So when we add it to the 2y, there's no more 2y.
Multiply by negative 2.
There you go. So negative 2 times row 2, adding it to row 1, makes the new row 1. So the third operation makes zeros. Off to the side, let's write down what negative 2 times the second row looks like. So this row here, 0, 1, negative 3. Off to the side, we'll multiply that by negative 2. We'll get 0, negative 2, positive 6. We're going to take those new numbers in green and add them to the corresponding first row. So 1 plus 0 makes 1. 2 plus negative 2 makes 0. That's what we wanted. And negative 5 plus 6 makes 1. And I'll put in the old second row. We got to our goal, which is great, which means now we could read this back as equations. The first one technically says 1x plus 0y. Well, that's just the same thing as x equals 1. Second row technically says 0x plus 1y. That's the same thing as y equals negative 3. So the ordered pair 1, negative 3 satisfies both equations. So what took us 20 minutes? We could have done in about 5, but this was more fun. Sorry, not sorry. To be honest, major C's aren't essential really until you hit 4 variables or so. So we just have to enjoy the process for now. All right, so one more time. Do one column at a time, start on the left, make your 1, then make your 0. Move on to the next column, make your 1, and then your 0. Repeat until you've hit all the columns. Okay. Now there are scenarios to where things can go bad. I'm only going to say this just in case it's in your homework. But if during the process you get like a row of zeros, it doesn't matter where that row of zeros is at. It could be the first row, last row, middle row, doesn't matter. If you get a row of zeros, you're in a special case, and it's just like 9.2. The example on the left technically is saying 0x plus 0y plus 0z equals 5. Which means 0 equals 5. But 0 doesn't equal 5? That's crazy talk. So if all of your variables cancel, just like we said in 9.2, and you get something false, then there's no solution. But on the right, notice it says 0x plus 0y plus 0z equals 0. This says 0 equals 0, which is true. So you would say infinitely many solutions. That is just something to say in passing. Just an FYI, just in case it's in the homework. Okay, questions? All right, that is 9.3. Did I write that right? Yes. All right, good. So now we skip to 9.8. 9.8 is partial fraction decomposition. Oh my gosh. Oh, side note, I forgot to mention this. In 9.3's text, they're going to talk about two methods. Gauss-Jordan, what we did, and this other thing called Gaussian elimination. Completely ignore and pass over the Gaussian elimination. Just focus on Gauss-Jordan. So unfortunately, we're in the part of the class to where I don't follow exactly what the book is doing because there's some things that are unnecessary. So that's 9.3 is the first of that. 9.8 is the second of that. In 9.8, before we actually get into the good stuff, let's go back to way back when you were all younger and cuter and you had 1/2 plus 1/3. In order to do this, you need a common denominator, and that would be 6. So you would say 3/6 plus 2/6 is 5/6. And then you would pay a quarter for a little thing of milk and have some cookies and then take a nap because life was great. Okay, now we're going to go the other way. I'm going to give you 5/6, and I'm going to ask you to break it down into fractions where the denominators can't be simplified anymore. And that's what partial fraction decomposition means. You're given a fraction and you're breaking it down into parts. This is going to be important in Calculus 2 when you do the scary thing, integration. Oh my gosh. There are 4 cases in this section. We are only going to do the first 3 because the 4th one is absolutely insane. So don't worry about that. The way to do this is by going through the examples. Now, as mentioned, I'm going to break from the presentation that's offered in the book. The book is not wrong at all. I'm just going to present it more as I don't want to say a flow chart, but that sort of approach to break down the cases. So let's suppose we start with, and I really should have prepped this because something about seat of my pants. Suppose we had 2x plus 1 over x squared plus 3x plus 2. This might turn out terribly. Let's find out together. The first thing to do, if it's not done already, is to factor the denominator. X squared plus 3x plus 2 factors as x plus 2, x plus 1. The factorization of the denominator shows us what case we are in. The name of the case we are in is non-repeating linear factors. This section has a little bit of chapter 4 in it because two important terms come back. Let's talk about those now. Non-repeating means that the multiplicity is 1. And notice these are both to the first. So non-repeating means multiplicity is 1. Linear means the degree is 1. So those are both x to the first. Please note, multiplicity has no relationship to degree for what we're doing here. So do not confuse the two. Okay. The way this plays out is that because the multiplicity is 1 for the factor x plus 2, that means the factor x plus 2 will get one fraction where x plus 2 is in the denominator. Because the multiplicity for x plus 1 is also 1, that means there will be a fraction whose denominator is x plus 1. So the multiplicities dictate the number of fractions. Meaning if one multiplicity was a 3 and the other one was a 4, then there'd be 7 total fractions. I will not be giving you 7 total fractions. I have better things to do. And I'm assuming you do as well. So that's the second step. First step, factor the denominator if it's not already factored. Second step, write out the denominators of the fractions. The third step, be very careful with the terminology. The third step, the numerator of these fractions has one less degree than the factor's denominator, factor's degree in the denominator. And I will say that again. I don't know what I just said. The degree of the numerator, is one less than the degree of the factor in the denominator. The degree of the denominator in the first fraction is a 1 because it's x to the first. 1 less than 1 is 0. So the numerator's degree is 0, which means it's just a number. We don't know what that number is. That's the point of the problem. So we tend to use letters. We'll use capital A. Oops. The degree of the factor in the second denominator is also 1. So the degree of the numerator of that factor is 1 less, which is degree 0, which means it's another number. We'll call it B. Did I say the word multiplicity at all? No. So determining what goes in the numerator has nothing to do with the multiplicity. It's all about the degree. So our job is to figure out what A and B are. Side note, they could be pretty integers. Like here we had 1 and 1. Awesome. They could be fractions. They could be positive, negative. Anything's possible. Okay. So this is our setup. Your next step is to multiply everything by the LCD, which is x plus 2, x plus 1. So in other words, we're going to clear out all of the fractions. On the left, the entire denominator cancels out, and we are just left with the numerator 2x plus 1. On the right, for the first fraction, the x plus 2 factor cancels, and we are left with a times the quantity x plus 1. I'm writing out every step. If you wanted to distribute your a through, cool. I'm writing it out because it's our first time doing this. For the second fraction, the x plus 1's cancel, and we are left with b times the quantity x plus 2. Okay. This next part's a little bit of algebra. If we distribute the a through, we get ax plus a. And distributing the b through, we get bx plus 2b. Rearranging terms on the right, I'm going to put the terms that have an x together, and I put the terms that have that are constant together. And then from the first two terms, I'm going to pull out an x, and the next two terms, I'm just going to leave those alone. I'm using colors on purpose to help emphasize what's about to happen. So all I did was I pulled out the x. On the right, the coefficient of x is the expression a plus b. On the left, the coefficient of x is 2, which means that a plus b must equal 2. The coefficient on the left must equal the coefficient on the right. Likewise, the constant on the left is a plus 2b. The constant on the right is 1, which means they have to be equal. So now you can see why this section is in this chapter, because we need a system of equations. Now, from here, you can do substitution, you can do elimination, totally fine. I'm actually going to show you how to do this via the calculator, which I will allow you to solve a system only in 9/8 using the calculator. If you go that route and you're not going to do it by hand using substitution elimination, I at least need to see this system. That would be your work for me. But after this, you can use the calculator. But first off, questions on clearing out the fractions and eventually getting to the system. Okay. Do-do-do, be-do-do-do. Taco Tuesday. Did not have tacos today. It's a shame. Okay. To get this into the calculator, what we're going to do is we're going to create a matrix. And you'll notice above the inverse key is the word matrix, and it's the same color as the second button. So we'll go to second matrix. You might not have anything here, totally fine. You could always overwrite one, or you can just go to a blank space. It does not matter. I'm going to scroll over to edit. And I'm just going to go to a new one. I'm going to go to G and hit enter. We have two equations. We have an A, a B, and a constant, so 3 columns. So we're going to need a 2, enter, 3, enter matrix. One A plus 1B equals 2 is the row 1, 1, 2. 1A plus 2B equals 1 is the row 1, 2, 1. So one more time, second matrix, 1 over to edit, put in the dimensions of the top, and then put the coefficients constant below it. Once you have that, second quit. In the TI series of calculator, there's a lot of menu diving. So second matrix one more time. Scroll over to math. Scroll up. And you're looking for this thing called RREF. Ravenous ravens eat fish is exactly what that stands for. It has nothing to do with math. It's really weird. Hit enter. And then we have to tell the calculator what matrix we're applying this to. So for the last time, second matrix, and this time under names, select your matrix. You could hit the number 7 for me for G, or you can scroll down and hit enter. Oh my God, that worked out very nice. We could have gotten fractions there. We didn't. We're good. So notice, because A was the first column and B was the second column, this is saying A is 3 and B is -1. So to finish this off, we would have 3 over x plus 2 plus -1 over x plus 1. And the reason that is because originally we put A over x plus 2, we put B over x plus 1. All right, so that's pretty much the process for the whole kit and caboodle. Factor your denominator if it's not already factored. Break it up into fractions. Clear out all the fractions. Create a system. RREF the system. And that was case 1. We won't do a full case 2 and a full case 3. We'll at least get up to this part today, because I had 3 coffees. It's not going to help. Okay. Case 2 is when you have repeating linear factors. Repeating means your multiplicity is no longer 1, it's bigger than 1. Linear means your degree is 1. The multiplicity dictates the number of fractions you have. Because our multiplicity is 2, we will need 2 fractions. And the way this works is you count up to the multiplicity starting at 1. What I mean by that is we'll have one denominator that is x plus 3. And then we'll have another denominator that is x plus 3 to the second. This counting up that I mentioned is because the first denominator is technically x plus 3 to the first, and then the second denominator is x plus 3 to the second. But we just don't write the parentheses to the first. There's no need for that. But do not get tripped up over multiplicity and degree. The degree is still 1. So the numerator's degree is 1 less. So 1 less than 1 is 0. So this numerator is an A. And 1 less than this one is 0. So this numerator is a B. That 2 is a multiplicity, not a degree. After this, multiply to clear all the fractions, make a system, RREF. As a matter of contrast, just making this up. Hi. I'm teaching class. Do you want to say hi? No? We're doing partial fractions. No? He's not interested. As a matter of contrast, how many fractions would we need for this problem?
Would it be 3?
It would be 3. Very good. Because notice, this is a 1 here, and that's a 2. So the first denominator will just be an x, and the next 2 denominators come from the x minus 2, where we count up to the 2. So x minus 2 and x minus 2 squared. All 3 factors are linear, which means all 3 numerators are constants. So in this case, we'd have an ABC. But after that, same. Clear out the fractions, create a system, RREF. Case 3 is non-repeating quadratic factors. Oh. How do I want to do this? Oh, I should just look at my notes. Wouldn't that make most sense? Yeah. X squared plus 9 does not factor using real numbers. It's actually x plus 3i, x minus 3i. So that's why it's a quadratic factor. It doesn't break down using real. This will need two fractions. And again, it's about multiplicity. The multiplicity of the x plus 2 factor is a 1. The multiplicity of the x squared plus 9 factor is a 1. So we need two fractions. One for each factor. The first denominator we can say is x plus 2. So that's what we did in case 1. Not really crazy there. The second denominator we could say is x squared plus 9. Very similar to case 1. Because again, the multiplicity dictates the number of fractions. Here's where it's different. Well, I lied. Not yet. Since the first denominator is a 1, the numerator will be 1 less degree, so 0. So we can just call that a. But the second denominator's degree is a 2. 1 less than 2 is 1. So that means the second numerator is linear. So we write bx plus c. That's the only change. After that, set it for the 5th time, multiply it by the LCD, create a system, RREF. A lot of cheering. Couple of comments. The order in which you write the fractions does not matter. So if your first fraction was actually a denominator of x squared plus 9, you may have the numerator as ax plus b if you're going alphabetically, and then you'd have c over x plus 2. When everything is said and done, when you find your a, b, and c and put them in the proper fractions that you put, our answers would be exactly the same, even if you put them in a different order. And that's because multiplication and addition are commutative. So if you're following along to the video and I factor differently than you, doesn't matter. Our very final answers should be the same. Comment number 2, I don't remember anymore. It's gone. There are, I remember comment 2. There are 1, 2, 3, 4, 5 example videos for this. But again, they're all the same. The only hard part is this setup. One thing I will tell you is that in order for any of this to work, these fractions have to be proper. And proper means that the numerator's degree is less than the denominator's degree. Heads up, I think one of your homework problems is improper, which means you get to remember how to do long division, section 4.3, and then to make it proper. So enjoy. Happy Thanksgiving. Happy third night of Hanukkah. Whatever. All right. That is 9-8. Let's talk about 10-1. Parabolas. I'll just discuss it because, again, short on time. I don't want to keep you too long. What we're doing now is, we talked about parabolas already in chapter 2. However, those were rectangular functions, meaning they pass the vertical line test. The ones we're going to do in this section need not be rectangular functions, which means instead of just opening up and down, they can now open left and right. So there's a slight change. One more time, the way the book presents things, totally fine. I'm just going to present it as if you needed to count. There are formulas for this. Formulas for this section and the next 2 sections are provided for you on the test. It's just a matter of knowing how to read them. the way a parabola is defined, and the one I'm going to draw is one that opens up, but this could be also down, left, or right. The way a parabola is defined is that every point on the parabola is the same distance away from a point called the focus and an imaginary line called the directrix. And what that means is if I pick this point here and my drawing is totally not to scale, the distance from the focus to that point and the distance from that point to the directrix are the same. And that's true for any point on the parabola. So my parabola should actually open up a little bit wider so you can see that better, but what are you going to do? We are going to have we're going to have 4 types of parabolas. The first 2 have the vertex on the origin, and the other 2 have the vertex somewhere else. So if you remember back in 1.1, we had H and K for our circle. Same deal. They come back to say hello in this chapter. Apparently they're British. In order to understand the formula for a parabola, I'm actually going to redraw this real quick. There's a very important letter associated with our parabolas in this section. Let me redraw this. I had to draw a little bit bigger. And that letter is P, lowercase p. P is the distance between the focus and the vertex. And P is also the distance between the vertex and the directrix. So if you know the value for P, what we're about to see is you can get the equations of parabolas centered at the origin, or vertex of the origin, however you want to say that. We're going to make a little chart. And this is the chart that's provided for you on the midterm. So you just have to basically know how to use it. As a comment, we don't have time to get into the derivation of the problem. It goes back to the distance formula. I think it's in a book. So if you need some nighttime reading, there you go. If you have a vertical parabola, that means it opens up or down, and the vertex is at the origin, then the formula is x squared equals 4py. If you have a horizontal parabola, meaning it opens left or right, and the vertex is at the origin, the formula is y squared equals 4px. Now these are all labeled for you. It's going to basically look like this on the chart, but if you're not looking at the chart, you know it's vertical if the square is on the x, and you know if it's horizontal if the square is on the y. That is the watered down version. Before we do the second row of this table, let's quickly jump to an example. Let's suppose I wanted to draw y squared equals 12x. Let's break this down. square is on the y, which means we have a horizontal parabola, which means it opens to the left or to the right. The coefficient of x is positive, which means it opens in the positive direction horizontally, which means to the right. So we have a right-facing parabola. The way I'm teaching this is about counting. The book has some formulas to determine the location of the focus and the directrix. They're not wrong. I'm not providing those formulas for you only because if you can count to 10, that's all you need to know. So real quick, one more time, squares on the y. The coefficient of x is positive. We're opening in the positive horizontal direction. Oh my gosh. Pretend that looked better than what it does. P, regardless of how the parabola opens, is always the distance from the vertex to the focus. Our vertex is at the origin. The focus is always inside the parabola, and it's given by p units. Well, if the coefficient of the linear side is 4p, that means that our 12 is really equal to 4p, which means p must be 3. So from the vertex, because the parabola opens to the right, we move 3 units to the right to find the focus. So that puts us at the ordered pair 3, 0. Because we traveled p units. The directrix is an imaginary line that never touches the parabola, and it's in the opposite direction of the focus. So for the focus, we went 3 units to the right, which means the directrix would be 3 units to the left. Here, when it's a horizontally opening parabola, our directrix is a vertical line because, again, it can't touch the parabola. 3 units to the left of the y-axis is the line x equals -3. So notice what we didn't do. We did not make an XY chart. We did not plot a bunch of points. We plotted the vertex. We sketched the U-shaped curve. And then we put where the for the focus and the directrix is. That's about it. If we wanted a more precise graph, yeah, we would totally do an XY chart. Waste of our time. Questions? Okay. The other version is the vertex at another point, HK. Just like in circle land, H is always with X, K is always with Y. It is no different than before. So the formula for the vertical parabola at HK is x minus h quantity squared equals 4p y minus k. And again, h is with x, k is with y, so be careful with this next one. Y minus k quantity squared equals 4p x minus h. Actually, I'm going to duplicate this page. Okay, let's put that to use. Because I want to contrast this example here with a similar one. Let's suppose we had y minus 3 quantity squared equals 12 times x plus 2. You only need to know what h, k, and p are to sketch the graph. H is always with x. The generic form is x minus h. We have x plus 2. So what is our h?
-2.
Excellent. K is always with y. The generic form is y minus k. We have y minus 3. What is our k?
3.
Excellent. And as before, the linear coefficient is 12. The linear coefficient is always for p. So one more time, p is 3. Side note, p does not have to be an integer. It could be a fraction. It could be negative. Any of that stuff. And you'll see that in the examples. I think one of them, p is 1/4. And that's squishy. So your vertex is given by hk. So our vertex is -2, 3. Square is on the y, which means it's horizontal. P is positive, so it opens positively in the horizontal direction, which means to the right. So away from Beyonce. When you move away from Beyonce, you get lemonade. Everyone knows this. Focus is always inside of the parabola. And we move 3 units in the same direction the parabola is opening. So if we're at -2, +3, and we move 3 units to the right, what ordered pair do we end up with?
Would that be 1, 3?
Excellent. So that means our focus is at 1, 3. Because we want p units to the right. Now if we go p units to the left, we'll get the directrix. The focus is at -2, 3. If we move 3 units to the left, we'd be at -5. Remember, a directrix is a line. So namely, it's at, pretend that's a straight line. It's at x equals -5. So the reason I wanted to do this was just to say, hey, it's exactly the same thing that we just did in the purple one. The only thing was the graph got shifted over. 2 units to the left, 3 units up. Same shape, opening the same position. If instead of that 12 there, it was a negative 12, it would open to the left. Because it's horizontally, squares on the y, in the negative direction, which means to the left. Now there are a bunch of examples to watch of more types of graphing like this. I do want to take a couple more minutes, if that's okay, just to talk about things you are also going to see in the homework that's related to this good stuff. So let's suppose we had, I don't know, hold on. Oh no. Oof. Don't write this down just yet. Wait for it. That's good. When one of the variables is being squared for our purposes, you got yourself a problem. The bad thing is, this does not look like any of those formulas that we have down here. So we have to get it into that form. The way we do that is by our trusted technique, completing the square. Remember that thing you wanted to never do again? It's coming back to say, hello. I know. I saw that. So the way we complete the... You can nod, you can shake your head all you want. The way we complete the square, yep, is we have to get the x's by itself and move everything else to the other side. I cannot believe this is going to work out. I'm so happy. The reason that we are isolating the x's is because that's the one that has the square, and that's where we need to complete. So remember to complete the square. Once the variables are isolated, and the leading coefficients of 1, which it generally will be for a parabola, you take half of the linear coefficient, half of 2 is 1, square it, 1, and add that to both sides. So we're going to add 1 to both sides. The left-hand side is x squared plus 2x plus 1, which factors as x plus 1 quantity squared. The right-hand side is negative 4y plus 8. We're almost to the form we need it to be in. Notice on the right-hand side, I could factor out a negative 4. The reason I'm factoring out a negative 4 and not just a 4 is because to make it into our special form, each variable needs to have a coefficient of 1. So now it looks how it needs to look. We're almost done. I do apologize. I really did have 3 espressos today. It's not gonna. I'm gonna be up to like 6 in the morning, but that's okay. Worth it for you guys. So because it's in this format, we can find our h, our k, and our p. H is always with x. So let me just, for side by side, write this down. What is our h?
Negative 1.
Very good. What is our k?
2.
Good. What is the speed of an air? I messed up the joke. Darn it. What is our P?
1.
Careful. Negative 4 equals
negative
4P.
1.
There you go. Very good. What direction does it open? Up, down, left, or right?
What do you mean to the left?
No. Square
So
is
that-
on... Yes. Square is on the X, which means it's vertical, so up or down. P is negative, which means it must be down. So just really quick. So our vertex is at -1, +2. We know it opens down. Focus is always inside of the parabola in the same direction. So from the vertex, we'll move down 1 unit, because that's given by P. And so our focus is at -1, +1. The directrix is in the opposite direction. So we moved down 1 for the focus, which means we move up 1 for the directrix. Careful, what's the equation of the directrix? And make sure you give me an equation, don't just tell me a number.
Y equals 3.
Y equals 3. Very good. So one more time, just do it by counting. That is how I'm going to also be teaching the next 2 sections. Everything the book is saying is fine, but they have formulas like H plus P comma K is the location. Oh my gosh. Nobody does that. Crazy people do. The ones that put mayonnaise on their pizza, insane. Avoid them at all costs. The only other thing is there are applications, and I think I have a couple of videos for that. The comment is that when you're doing your applications, absolutely only use the equations that are centered at the origin. The reason being is if you use the other two, then you're creating 2 extra letters, H and K. Way too much work. And then because that you are focused only on the origin, then the only unknown letter would be P, which saves you a lot of work. So as a super quick example of an idea of what you're going to do, let's suppose we had a parabola that opened up. The vertex was at the origin, and it went through the point 2, 5. I know, Marsh, we're almost done. We're doing parabolas now. We're not doing partial fractions. I know, you missed that part. And they want to know the equation of the parabola. So let's break this down. Vertex is at the origin. Awesome. No H, no K. Parabola opens up. Awesomer. We know it's a vertical parabola. Those two combined mean we must be looking at the formula x squared equals 4py. Because it opens up, we should expect p to be a positive number. So all we need to do is find the coefficient of y, and then we're done. Well, if it goes through the point 2, 5, that means when x is 2, y is 5. So let's solve for p. 2 squared is 4. 4 times p times 5 is 20p. Dividing both sides by 20, we get 1/5. Which means our formula is x squared equals 4 times 1/5 y, or x squared equals 4/5 y. That's pretty much how every single word problem is done in this section. Very similar process for the next 2 sections. So again, keep it centered at the origin. It usually does not matter if it's up, down, left, or right, but keep it always positive when you're doing your drawings. And then you need to just find p is basically what's going on. The comment to make is, as far as real life applications, if you think about headlights in a car, typically what happens is they purposely put the light bulb. I know this is not what light bulbs look like anymore. They purposely put the light bulb at the focus, and they make the parabola a mirror. So when the light beams out, it hits the mirror and shoots out directly ahead. That's basically how parabolic mirrors work, or light sources work. So when it's like, oh, how far should the focus be? Where should the focus be? Where should the light bulb be so that the headlights work? Blah 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 words. That just means find p. Likewise, on a receiver for like a satellite dish, they put the receiver at the focus so that when a source comes in, it hits the dish and bounces to the receiver. Where should the receiver be put? Blah, blah, blah. Who cares? Find p. That's all basically these word problems are going to be saying. All right. That's enough torture. Good news, everyone. Next week is our last week of lecture. 3 more sections. More drawing of pictures. Huzzah. But as a reminder, 2 weeks from tonight is your final. And the way to study for that is to redo all 4 practice tests. Also redo your midterm. And then let me know what questions you have. That's really about it. All right. If there are no further questions, thanks for sticking around. I appreciate your time. And I will post this video in a couple hours unless I fall asleep. All right. Bye.